Hello everyone, this is Eric Tanner speaking, and I'm going to go over my research for this semester's project. This should serve as an extension of my previous security presentation on the CAN bus protocol. This research I'm entitling Security Analysis and Solutions for CAN bus and FlexRay Protocols in Automotive Applications. I have a lot of material to cover, so I'm going to try to go through everything pretty quick so I can cover all the details. So my main motivation for this research was that I've seen that CAN bus and FlexRay protocols can be vulnerable, and I wanted to look into them a little bit further to understand how they work and look into algorithms such as DES and AES for securing them. I wanted to understand what their threats were and vulnerabilities, and then understand that enough to be able to make solutions for securing these buses, and also come up with a hardware platform that these can be implemented on. So I decided to constrain this research to just block cipher style encryption algorithms. On the right you can see a diagram which shows how these work. There's a plain text entry and a key that get fed into a block cipher, and the output of that is the encrypted ciphertext. I looked into DES, which is the data encryption standards. This is a 64-bit block size and a 56-bit key. And then AES, which is advanced encryption standards, 128-bit block size with variables of 128, 192, and 256-bit keys. These are both symmetric key algorithms, which means that the same key is used to encrypt and decrypt the data. And the goal here is to just make sure that I'm doing a good balance between performance and security. So I wanted to make sure that I wasn't picking an encryption algorithm that was way overkill, because that will definitely impact the performance. As we're all familiar with, the CAN bus, it's a multi-master, multi-cast bus. It's differential paired with a non-return to zero or NRZ encoding. The maximum capable data rate is 1 megabit per second, and typically these buses are run around 125 and 500 kilobits per second. The main thing here I wanted to harp on was the arbitration identifier field. In my last research, it was shown that this arbitration identifier field was used for denial of service attacks, and that you could create high priority messages by setting this field to 0 and flood the system, creating so much traffic that the bus can no longer operate as designed. So my solution for the CAN bus would be a two-step solution where, one, I'm going to encrypt the data field of the message, and two, I want to add a start header, arbitration identifier, and data link in the first message, and the second message include the actual data. This is going to encapsulate all these parameters within two messages. Unfortunately, that's slower, but it's going to make a more secure solution. For this, it works out great to use DES because it's a 64-bit cipher and a 64-bit ciphertext, so I wouldn't have any data growth with my algorithm. This was a good balance for the security and efficiency, and it's great because it maintains the CAN bus protocol where legacy devices would still be able to operate on the bus. And ideally, I wanted to mention that I think this should only be used for necessary messages that need to be secured. Otherwise, I think the bus should operate, as normal, and only implement this for messages that need to be secure. So FlexRay, somewhat similar in that it's sending messages, but this protocol was meant to be faster than CAN bus. It has a couple different network topologies. There's passive, active star, and standard bus. I mainly looked at standard bus for this application. Um, each node has a host which deals with the application layer, a controller for data link layer, and there's two transceivers for the physical layer. This is a two-channel protocol. The data rates are also dependent on this scheme for the two channels. So you can get up to 10 megabits per second on the redundancy mode, where this is transmitting the same data on both channels so that you can have error control. And then the 20 megabits per second would be in simultaneous mode, where data is transmitted simultaneously on both channels. This is a time division multiple access scheme, which is kind of a schedule of messages. And there are 4 main events that happen. There's the static segment, network idle time, dynamic segment, and symbol window. The dynamic segment is where I wanted to focus, because this is the segment for event-based messages, such as an airbag goes off, or engine codes. This would be based off an event, so this is where I want to propose the solution. So for the FlexRay solution, I want to do similar to the CAN bus solution, where I'm going to encrypt the data field of the message, but also add a start header and a length in the first header for this. For this protocol solution, I've just really wanted to prevent message spoofing, which could be done in this dynamic event time. This could be a dangerous area if messages are spoofed, and this, just in general, I think would be a better solution for securing the FlexRay bus. I looked into, since we have a much larger data field here, I had to look into AES-256, which creates a 256-bit ciphertext. So in the scenario of the largest FlexRay message of 256 bytes, you would need 8 block cipher conversions to transmit all the data. So this is going to definitely impact the performance. So this is the architecture that I came up with. I went with an FPGA-based architecture that acts as a co-processor to the ECU. I chose an FPGA because it would be much faster to do these encryption algorithms inside of an FPGA versus doing it inside the ECU or a microcontroller. What the concept would be here is that the ECU would pass the data contents from the message to the FPGA for encryption and decryption, and then the ECU would still talk to the bus as it normally would. So this is a summary of data from my research and from some references noted here in 6, 7, and 8. The trade-offs are between a Spartan 3E and one that I chose, which was a Microsemi Igloo 2 flash-based FPGA, both comparable in size. So this AES-128 algorithm fit within 2400 LUTs and 320 VRAMs. So it is obviously going to work for the DES algorithm on CAN, and these parts could be used for that. It could also be used for FlexRay, but you'd probably only be able to fit 2 AES-256 blocks within this device. This could work and still get you good performance probably, but the ideal scenario for the FlexRay would be to use a bigger part, so you could do 8 parallel AES-256 blocks, so you could really increase performance. Unfortunately, you would take a hit on power in that scenario, but that would be an industry trade-off, whether or not that would be worth it. For power consumption on these algorithms, it really could go from hundreds of milliwatts up to watts. It's highly clock rate driven and design complexity driven, and ideally these designs I think are feasible, but I'm not sure if the industry will adopt them. I really enjoyed this research, and hopefully if you guys have interest in learning much more details than I was able to discuss here, read the paper that I'm putting out here on the website here soon, and post any questions if you have any. Thank you.